Okay, so I welcome all the audience and good day to one of you. I would speak more specifically to those participants in the leadership program webinar and then workshop, but I know that you are much more online attending this interesting series of lectures. So thank you, Rob, for introducing me and for having offered me this opportunity to present a couple of lectures in the frame of this leadership program. As you can see from this slide, some excerpts from the syllabus of the course we are intending to propose to the participants. I will give 3 lectures, one in the frame of this present webinar, an introduction to radiation chemistry, introducing ionizing radiation, the different types, their main properties, discussing some metrics of radiation processing in terms of penetration, energy deposition, and then moving gradually to the chemical effects induced by radiation into matter, particularly into organic matter, and then provide a very simple overview of the effects in solid, liquids, and gases. During the workshop in person in our university in Reims, France, there will be other lectures covering more advanced radiation chemistry and then radiation chemistry applied to polymers, and then industrial polymer processing, while other lecturers will have aspects, particularly aspects covering the sterilization applications and the use of different types of facilities which are available at different industrial sites.
Xavier,
so
sorry
just
to
a forward
interrupt.
Before start. Yeah.
Perhaps you could, Xavier, you could switch off your camera.
Okay, maybe. But I've lost the Teams. So, okay, here I switch this.
Okay, thank you.
So do you see my screen?
Yes, we do.
Okay, so a foreword about the program. So especially for the audience, the large audience, which covers a broad spectrum of background, likely very different professional experience and different technological or business interest. So please note that this lecture has been targeted and designed to meet the IAEA's leadership program goals. So you might hear or read during the course information that is already known by you, or that seems useless to you, or maybe that seems too specialized for you. So I'm very sorry about that. But the moderator, and particularly Professor Edgecock, will take note of the questions and comments, and we might discuss different points by the end of this lecture. And of course, for the participants to the leadership program, we will interact more closely during the leadership workshop. So I already mentioned the main outline of this lecture, and I will start by just defining high energy radiation. So of course we have radiation which are described by physicists with a duality according to quantum mechanics, either as particles or as photons, but these are of course different features, and we typically have the 2 classes, atomic and subatomic particles, electrons, protons, or heavy ion, and that are electromagnetic radiation, which applies to X-ray or gamma ray. The second term is the high energy. This qualifies radiation carrying energy higher than the threshold able to expel electrons from atom shells. So to cationize atoms, and this happens, for example, for the hydrogen atoms with energies above 13.6 electron volts. For other atom, the threshold energy depends on the atomic charge number and on the mass number. So it is also known as ionizing radiation, but it's much more preferable to speak of high energy radiation, taking this into consideration. So the different natures of this high energy radiation, they can be first photons of very short wavelength, down from vacuum UV to very energetic gamma rays, including X-rays. So this is the first time. So we refer to electromagnetic radiation. We also have light in terms of small weight particles, which can be alpha particles, which are helium cations, or beta, this means electrons, or even neutral, so without any charge, neutron, which can also interact with matter and consider as ionizing radiation. Swift heavy ions are the last class, which include, for example, such heavy ions like iodine 127 with N plus as a charge. These ions heavier than light hydrogen, proton, or helium 2 plus are not produced by radionuclides. These are produced or extracted from a source and then accelerated to extremely high energy. But all this radiation from class 1, 2, or 3 all produce ionizing effects. Their effects are strongly dependent on the number of charge and mass of the particle, and the penetrations and the mechanisms of energy deposition are very specific to the nature of the high energy radiation. So let's have a very brief overview of the main types of radiation sources. You have on the sketch number 1 a typical artist view of a cobalt-60 gamma facility, which includes a large number of cobalt sources, which are stored in a pool, in a water pool at the center of the facility. This is protected with a large amount of concrete, and by extracting the source and by moving different samples to be radiated in front of these cobalt sources, we can apply the desired radiation dose. This is a typical industrial facility, while on picture number 2, you have, you typically have one laboratory irradiator, which was designed typically in the 60s, 70s, which can be, of course, used for laboratory experiments of small size, and which are still present in a number of laboratories worldwide. Electron accelerators, as shown in picture number 3. This is a dynamitron, for example, of about 600 kilovolts, which can be installed in a facility, and again having different packages which are driven under the beam and all this also is implemented to induce the realization of cross-linking of different goods. And finally, number 4, when you have a typical benchtop low energy electron accelerator, which can be used in a research and development laboratory, and which is very compact, self-shielded, and doesn't need any additional protection, while the industrial facilities, of course, need large amount of concrete to protect the operators and the surrounding from the radiation produced or induced as X-rays from these accelerators. So the main features of these different types of sources are the penetration, energy deposition, the surface or volume which is treated by passing in front of the beam or being stationary placed in front of a beam, and the overall throughput of the installation. And as we have illustrated by the different pictures, we have industrial facilities which are really big and laboratory equipment, which are much compact and easily handled in small rooms. So interaction of high energy radiation and matter. We will first take the example of charged particles like energetic electrons from an electron beam, which will interact with matter by losing their kinetic energy in almost a continuous way through Coulomb interaction with the atomic orbital electrons and atomic nuclei. This takes place through collision and radiative losses, and also by scattering. This means with the change of direction of motion of the incident particle. So the two main consequences of these interactions are, in red, the ionization. This means that the interaction with the electron and the orbital electrons will expel another electron, while the incident electron will continue its way with a lower amount of kinetic energy. And the second pathway is the excitation, where by passing by the electron shell, the incident electron will induce a promotion of the energetic level of the electron which was around the atom. And this promotion to this sometimes anti-bonding orbital will then induce a cascade of decay of the energy with release of X-ray or photons to relax these excited state. So these are the individual events, but one has to take into account that the initial particle has a tremendous amount of energy, and we can see that the incident particle will interact a large number of times by depositing energy with a single ionization or excitation events, but can also induce the formation of a number of ionization or excitation in clusters or spurs, and even in some cases induce the ejection of a fast electron, which can be called a delta ray, which will induce again another cascade in another direction from the original pathway. So typically, to summarize, we can see that these energetic electrons will produce X-rays and or gamma, which will induce ionization, and this will end up with the formation of fast electrons. While we are considering now the high energy photons like X-ray or gamma rays, which can deposit their energy by three mechanisms. The first one is the photoelectric effect. So the incident photon will completely lose its energy to expel a photon. In another procedure, the Compton scattering will see that the initial photon will be scattered after interaction with an electron, will induce the ionization, and then we will continue to have this type of processes by the photon, which continues its route, and by the electron, which has been expelled from the orbital shell of the atom. And then the third mechanism is the pair formation, which consists in the simultaneous formation from the interaction from the photon and the nucleus of a positron and electron, which might recombine at another stage of the process. The relative importance of the three basic types of interaction depends on photon energy and on the electron density in the target material. And the scheme below shows the distribution of these different mechanisms as a function of the atomic number as an ordinate, and in abscissa the energy of the gamma ray in a logarithmic scale. And we can see that at rather low energy, the photoelectric effect is dominant. At extremely high energy, we have pair production, but in the medium range, we can see that the Compton scattering is the main mechanism, particularly with the gamma ray energy at around 1 mega electron volt, which is very common with the cobalt-60 sources. So we can conclude that ionizing radiation produces myriads of secondary electrons, whatever the original radiation interacting, I mean, particle or photon of high energy. This will result in the formation of secondary electrons that rapidly slow down, we call about thermalization, to energies below 7.4 electron volt, which is the threshold to produce electronic transition in liquid water. For the primary charge particle and the secondary electrons, the gradual decay in energy proceeds by a sequence of discrete events. But we frequently use the concept of stopping power of the linear energy transfer, which is the quantity representing the decay in energy by a continuous function. This means that we are using some approximation describing the phenomenon as a continuous slowing down process. So depending on the amount of energy transferred to the electron, the atoms or the covalent assembly of atoms, meaning ion molecules, molecular ions, can undergo ionization, excitation, and then some thermal transfer to the surrounding medium by collision and vibration. This physical stage typically takes place within 10 to the minus 15 seconds after the onset of the interaction. So these are very, very fast processes. Let's speak now about some basic quantities and units describing radiation processing and the interaction with matter. For radionuclides like cobalt-60, the International System Unit is the becquerel. Becquerel is defined as 1 decay per second. This means the emission of one radiation from the radionuclide per second. And in practice, and particularly in the Cobalt-60 facilities, one uses the Curie unit, and more frequently kilo or mega Curie units, 1 Curie being 3.710 to the 10 becquerel, and it actually corresponds to the activity of 1 gram of radium-226. So this is for radionuclides. For now, from the side of the sample, which is subject to the irradiation, one typically speak about the absorbed radiation dose or absorbed dose of radiation, which is the quantity of energy deposited in matter by ionization or by the ionizing radiation per unit mass. One has to remember that this energy deposition is non-selective and does not compare at the absorption by molecular compounds of UV visible light, which follows very precise selection rules. In that case, energy deposition is essentially governed by the electron density of the substrate. So the dose unit is the gray. A gray is defined as 1 joule of radiation absorbed per kilogram of matter. Formerly, this was the unit was the rad or the megarad. The conversion unit being that 1 megarad is equal to 10 kilogram. One has also to take into consideration the rate at which the dose is deposited in matter, and we speak about the dose rate, d of dose over dt, which has to be considered as an instant value, and especially one has to consider the peak value if you have a pulsed irradiation source. And in that case, if this is not constant over time, we can use the average dose rate, which is the time average value, delta of energy deposited divided by the time of the irradiation. So the dose is, of course, a key parameter and a key specification for radiation processing, but I would like to stress that it's not the single descriptor of radiation processing. One has also to know the dose rate and that penetration to know over which range of depth this treatment is applied to the substrate. There are, of course, quantitative effects of the process which are directly related to the dose, but one also has to take into account the kinetic aspect. This means how this dose is delivered with respect to time. So dose is obviously a very important parameter, but it should not be considered as the single descriptor of a radiation process. Now we can also try to describe the way the energy is deposited inside the material, and we know that, of course, there is some attenuation, and this can be described for high energy photon beams like X-ray and gamma rays by a decreasing exponential variation, as suggested by this equation, where the mu parameter is the linear attenuation coefficient, which is a key component of this decay, and which allows to model the precise decay of the intensity as a function of the absorber thickness. For charged particles, electrons, alpha particles, or other type of ions, one uses the stopping power and the linear energy transfer. So this is defined as the elemental variation of the deposited energy as a function of the distance run by the particle. This is expressed from the well-known Bethe equation, which takes into account the nature of the radiation and, of course, the features of the atoms constituting the substrate subject to irradiation. And from this linear energy transfer, one can, of course, describe the variation of the absorbed dose as a function of depth. Sorry. And of course, it's very important in that domain to make measurements, but also to make calculation. And there are different modeling tools and simulations which allow engineers to design the treatment they wish to ensure correct irradiation of the goods to be irradiated in their depth. So, of course, and we have already mentioned that the different types of radiation have different cross sections with matter. This means that the attenuation of the penetration can be from very deep into the materials or to be stopped at the surface, depending on the type of interactions. And I have selected here just to compare, for examples, for small or laboratory scale radiation sources, low energy electron beams, at 100 kilo electron volts of energy, the incident beam will be attenuated to 70% of its initial value, that is surface value, at 110 micrometers, while for a gamma or X-ray, at this energy, of course, the photonic nature of these X-rays or gammas will have a much lower cross-section and will decay to half of their top value after 4 centimeters. So we see that there is a large difference due to the particle and charge nature of electrons compared to X-ray or gamma rays. And of course, as you raise the energy of the incident particle, whatever it is, a photon or an electron, you will of course increase the penetration and allow to have effective treatment in the range of 20 centimeters for X-ray of 3 mega electron volts, whereas for electron at 3 mega electron volts, you will treat about 1 centimeter of materials of unit density. Another main differences between industrial electron accelerators and industrial cobalt irradiators is the dose rate. I mean the dose deposited in matter per unit time. And we clearly see on the right-hand side that for electron beam, the dose rate can go up to hundreds of kilograms per second, whereas with the cobalt 60 irradiator, this is several order of magnitudes lower, with dose rates in the range of 1 to 100 kilograms per hour this time. And here we have different examples of depth dose deposition curve. On the top, these are for low energy accelerators from 75 to 300 kilovolts, and we find what's qualitatively said about the penetration of some 100 micrometers for 100 kilovolts. Of course, increasing up to 300 kilovolts. And the bottom graphs allows to give a comparison of the main types of radiation, comparing X-ray photons, electrons, neutrons, and heavy charged particles with their very different profiles of energy deposition, which of course take into account the presence of charge, the presence of mass in the incident radiation. And finally, to give you some ideas of the differences of LET, of linear energy transfers, this table shows that for electron, alpha particle, or iodine cation, we have again several orders of magnitude between the LET for the electron in nanojoules per meter. We are typically 32 10 to the minus 3, whereas we are 1120 for the heavily charged and heavyweight iodine cation. Well, dosimetry is important, of course, from an experimental point of view for performing radiation processing. This has been covered in the first lecture given by Yves Hénon 1 week ago. I will not enter into the details here, but just to mention that some dosimeters are based on typical physical processes like calorimeters based on graphite or water, which provide an indirect measurement of the amount of radiation absorbed by measuring the increase in temperature. We can also use ionization chambers, but also, and this is because I'm addressing here radiation chemistry, that many chemical dosimeters are very useful. So we are using those reactions induced by radiation to have changes in the UV visible absorption spectrum in particular, or sometimes in infrared, but UV visible is very common method for measuring changes in plastic films with dyes, or with some solutions like the Freaky dosimeter based on the iron 2, which is oxidized by the ionizing radiation. And finally, also the formation of free radicals, which is the basis of the measurement by electron spin resonance of the number of spins induced by radiation into this amino acid in the solid state. So radiation chemistry serving radiation processing through dosimetry. So there are important criteria for selecting a proper dosimeter. One has to consider the penetration of the beam, the dose rate, the dose range, ambient factors like temperature or humidity, and of course the need for precision, which might indicate which type of dosimeter would be more suitable for your purpose. Now, I would start to speak really about the chemistry, which is induced by radiation. And it's interesting to note that from a practical point of view, if we consider just the formation of free radicals, which can be produced by ionization of water, of hydrocarbons, different processes, but which will all end by the formation of free radicals. This means by chemical entities having a single electron in an atomic or molecular orbital, so the presence of a spin, and which are generally unstable species. All these free radicals can be used to perform sterilization, molecular chemistry, polymerization, polymer chain scission or cross-linking, oxidation, grafting. So and it is the art of the radiation processing engineer to select the most convenient type of radiation. Can use UV visible in some cases, electron beam, X-ray or gamma rays. We see that the nature of these can different, photons, particles, photons. The origins of this radiation are also quite different. Electrical power for UV-vis and electron beam, while radioactivity is at the origin of the gamma radiation. And their energies are quite different. So penetration is quite different. But in terms of efficiency, if we compare, for example, a solution containing a very efficient photoinitiator, which is irradiated by very powerful mercury lamp, like in a UV curing experiments, the number of radicals which are produced per unit volume here, cubic centimeter, and unit time is estimated to be 10 to the 21, which is 1 order of magnitude higher than what is typically observed by interacting fast electrons with organic matter, 10 to the 20, and several orders of magnitude slower for the interactions of gamma ray with here 10 to the 12 free radicals per cubic centimeter, and this is typically due to the rather low cross section of the gamma photons with matter. Now we have already spoken of the many applications of industrial radiation processing, and this was developed by Yves Hénon again in the first lecture of this series. Interestingly, industrial EB processes need less energy than most thermal treatment processes, and this is, of course, and this has been and is still a very strong advantage, which is exploited in this industry. Typically, the range of doses varies from about 100 gray to 1 megagray, depending on the application. And we can see that in the lower range of doses, this is typically by application to some food for preventing, for example, potatoes from sprouting, a little bit higher doses for disinfection, or even up to 10 kilogray for having surface treatment for chemical modification. And we can see at the larger values of doses, for example, for vulcanization of elastomers or cross-linking of some quite resistant thermoplastic, we can use doses higher than 100 kilogray. So large range depending on the application, and it's always there is always a trade-off to make between the desired effect and generally the degradation of other properties which might be also affected by the radiation treatment. Now, we have spoken about the very early physical processes that are taking place, especially by the interaction of electron or high energy photons with the outer shell electrons around the atoms. And we have already mentioned that this leads to excitation of, let's say, molecular arrangements, taking, for example, AB, which can be excited to AB star. Ionization would convert AB into AB plus dot, radical cation, plus an expelled electron. And also we can have a dissociative ionization of the molecular assembly AB into free radical A, cation B plus, and an electron. So the primary effects, which starts to be to induce some chemistry, is the thermalization of the electron. It means its gradual loss of energy to allow it to be solvated by the liquid around if we are irradiating solutions. So then we have the solvated electrons, which can have strong reductive properties. And for example, this thermalized electron can react with the molecular assembly AB to form a radical anion, AB minus dot. This is the electron attachment, or simply reduction of a molecular assembly. So the radical cation can also recombine with the thermalized electron, and seeing the energy of the electron is significant, the recombination ends up with an excited AB star molecule, which can further, and this is the last line, undergo homolytic dissociation. And we can also consider the possibility of radical cations to react with radical anions. So there is a charge transfer neutralization, which would end up with the formation of the excited states of both molecular assemblies, AB star, CD star, which can in turn undergo homolytic dissociation. This means that, as we have already said, most of this chemistry ends up with the formation of free radicals. Okay, to illustrate more precisely this, I have reproduced here the radial of water with very interesting features in terms of time frame. And I've already mentioned that the physical stage leading to excitation and ionization takes place typically in 10 to the minus 15 seconds. And afterwards, we have a physicochemical stage where a number of reactions take place, but in heterogeneous conditions. So these are heterogeneous kinetics, where these different primary products can interact with each other. For example, OH radicals, two OH radicals combining to form hydrogen peroxide, or the reduction of hydroxyl radical with a solvated electron to form the hydroxide anion, or formation of water by combination of OH radical and the hydrogen atom, and different things. And so all this takes place in a quite heterogeneous kinetics in the spurs, depending on the occurrence of the events. And one has to wait 10 to the minus 12 seconds so that this starts to be to allow for homogeneous kinetics after diffusion of the different species. And we end up with a number of different molecules, cations, anions, or radicals together with the solvated electron, which are the products of water radiolysis. But the main three species which undergo then the major part of the chemistry behind are the solvated electron, the hydrogen radical, and the hydroxyl radical. So to quantify the different chemical effects which are induced by radiation, one can define the G value, which relates to a particular radiation-induced event. The old unit was the number of events taking place for each amount of 100 electron volt absorbed by the substance which has been irradiated. Now we have to consider the international system unit. So the G of the given event, whatever it is now expressed in number of moles of events per joule of absorbed energy. We can convert, of course, easily from the old unit to the new one, typically by divided by the G event by 10 to the power 7, which would provide the G prime events, which is then expressed in the international system. So we will continue by sticking to this international system, and in this table you have expressed in micromole per joule the efficiency for the formation of the solvated electron, hydroxyl radical, hydrogen radical, so the three main species, and also some other byproducts. And we can see here that indeed the solvated electron and the hydroxyl radical are the most important species produced at intermediate pH values. So for whatever it is due to gamma or electron irradiation in this range of energy, at such pH, we have typically these values, whereas at very low pH, so high concentration in protons, we modify a little bit, we quench the solvated electron to the benefit of the hydrogen radical, and also if we have, if you are using alpha particle irradiation from a polonium radionuclide, again at low pH, we have again different distribution of the products, then the molecular products being the dominant one with hydrogen and hydrogen peroxide. So this is just an illustration of the importance to quantify the different products and to see the impact of different factors such as the energy or the pH of the medium. So by producing a number of solvated electron, one of course induce reduction reactions. So this happens with the carbonyl compounds, like for example acetone. So in presence of radiolyzed water, we would have then the solvated electron, which will be captured by the acetone to form a radical anion, which might then have its acido-basic properties and being converted into a free radical, a tertiary radical. Also, this can induce the reduction of metal cations, and this is one of the way to prepare metal nanoparticles like gold, silver, copper, or nickel by radiolytic processes. If we have some halogenated compounds like chloroacetic acid, the reaction with the solvated electron will induce the reductive elimination of a chlorine anion and together with a free radical, so that can be used to sensitize, for example, some polymerization processes by halogenated acids. Then we come to effects due to the hydroxyl radical. So here, on the contrary, we have an oxidative species, which will abstract hydrogen atoms from other molecules present. And for example, here, if we have polymeric alcohol. Typically, the hydroxyl radical will abstract an hydrogen on the carbon having the hydroxyl function, and this will in turn produce water and a tertiary free radical, which might evolve and undergo formation by dismutation, for example, formation of carbonyl group. And also here we have the addition reaction of the hydroxyl radical to and some acrylic acid, which would initiate the polymerization by adding onto the carbon-carbon double bond, and then will induce the propagation. And of course, free radical to self react to form, for example, hydrogen peroxide from the encounter of two hydroxyl free radicals. So these are just a couple of examples of what can take place from the reaction of different organic or metallic compounds in water. And this can be studied in more details by using pulse radiolysis, which is a very powerful technique allowing the researchers to study in detail the fate of the different species produced under various conditions. And by coupling pulse radiolysis with spectroscopy, real-time, so time-resolved spectroscopy in the UV or in the visible domain, one can monitor the different species quite precisely and to see the effects of different types of scavengers and to evaluate the nature of the mechanisms and also to provide some kinetic data, for example, about the effects of the nitrite anion upon the radiolysis of water. So this just to give a small example of what can be done using this type of techniques, which are more and more precise as new equipment and time resolution is improving decade after decade. Let's leave water to address organic liquids. And of course, each class of organic molecules has its specificities. We can just detail here what's the fate of cyclohexane upon irradiation. So the different processes we have described will form excited cyclohexane in probably a non-bonding orbitals for some of the electrons, which will then relax to form two free radicals, C6H11 and the hydrogen atom, or to form an cyclohexene, unsaturated, plus dihydrogen, and then different reactions between the free radicals and the original cyclohexane molecule. We can have hydrogen abstraction, and we can have also termination reactions by combination or by dismutation. And we can note here the formation of dihydrogen by two of the detailed reactions. And this means that hydrogen evolution, which can be quite easily measured by looking to the amount of gas produced upon irradiation, allows for a simple and useful mean for assessing the progress of radiolysis. And this is just to exemplify here that simple measurements can allow to quantify the progress of the radiolytic reactions. So I will not detail what's going on with alkanes, alcohols. We will have more lectures to come to describe the specificity of the different chemicals. Just here, just to mention that irradiating cetones with ketones, which can be solvents, so some solute. In that case, the ketones will form a radical cation and expel a pre-solvated electron. Same type of reaction with acetonitrile. So typically, the presence of oxygen or nitrogen as heteroatom is the location of the loose of the electron. Halogenated compounds, especially chloride here, we have different type of reaction. Again, the loss of electron comes from the heteroatom. And also we should mention here the very rich reactivity of aromatic compounds, which can now the coupling of the OH radical, which can attach and induce more complex reactivity around aromatic compounds. And this is very important in some environmental applications of radiation processing. So in brief, the radiolysis of organic liquids leads to take into account very precise structure reactivity relationship, which are due to differences in polarity, solvating properties of the medium. Also, we have to take into account the presence of energy sinks, which can reduce the overall response of the organic matter to the radiation. So these energy sinks can be double bonds or aromatics already present in the original compound or form during radiolysis. One has to take into consideration the hydrogen donating properties of the solvent or of the solute, because we have a lot of free radical chemistry which undergoes this type of hydrogen abstraction. And that we have the possibility to form not only neutral free radicals, but radical cations, radical anions, depending on the nature of the organic matter subject to radiation. Also, redox properties of the components have a strong influence on the fate of the initial compounds. So we are reaching 1 hour of lecture, so I will just give a brief survey that some of these applications of radiation chemistry can be applied to gases, and not only for basic research, also for environmental applications. And this will be probably illustrated by one of the coming presentations by Dr. Dagmara Chmielewska, and in their institute, they have developed a very interesting treatment of flue gases from coal power plants to reduce the amount of sulfur dioxide and NOx gases which are produced, and this can be done by irradiation, and they end up with the formation of fertilizers by combining this with ammonia. So very interesting process. And in solution, then we have to speak here about strong difference to be made between the direct and indirect effect of radiolysis. And in very dilute solutions, we have to understand that most of the energy is deposited in the solvent, which will be converted itself. So the solute will not react directly to the activation by the radiation, but by reaction with the byproducts of the radiolysis of the solvent, whatever this is, water, alkane, alcohol, or different alkyl halides. And this is illustrated here for a solution, for example, of nucleic acid, and this is of quite important for living material with biologic material, where the cells, of course, in the cells, the nucleic acid will be damaged both by the direct effects, but also by all the indirect attacks of oxidizing free radicals, which are generated in situ. So in solutions, important factors are the pH, the presence of oxygen, and the use of chemical scavengers, which can allow either to block a particular chemical pathway and allow for a more precise investigation of the mechanisms which are taking place in these processes. In the solid state, of course, there is a large number of applications which apply radiation to solid materials. Those could be frozen liquids and solutions, but this is typically for basic research to look at very, very low temperature, close to maybe 5 Kelvin, to see in organic glasses how what type of primary effects is induced by radiation. Of course, there are also technologies for welding or controlling metal assemblies, but this is very far away from our central domain of activities, where many substrates are polymers and composites for the purpose of sterilization, of cross-linking to have temperature resistant cable insulators, or to degrade radiation sensitive plastic to produce nanoscale transistor grids, for example, or to produce different types of composites without using an autoclave, which can be very energy consuming. And last but not least, one has to mention also the influence of radiation on metal oxides. For example, glasses, silica-based glasses will get colored and can be colored by radiation treatment, and with a much higher value, some crystalline minerals, which could be organic, which can be like diamond, or could be metal oxides, can get very nice colored to mimic natural gemstones. And this is also an activity, a commercial activity of interest. So yes, as we have seen, most of the chemistry which will be developed in further lectures will be based on the organic free radicals, which are easily formed. We know that we have reactions with oxygen, formation of hydroperoxide. This can induce polymerization reaction, but also scission and cross-linking. And it's important to consider the chain kinetics and all the different stages of the process. Besides, we have also very important redox chemistry, which takes place essentially in aqueous systems or in living systems, and also the existence of fast kinetics, which need precise investigation and which allow for a better understanding of the transformations induced by radiation. So I come to the conclusion. I wish that you take home simple concepts and images, essentially about the interactions between the different types of radiation and matter. Of course, in 1 hour, one cannot go into every and each detail. So take note of good references from literature. Have a look to some good books, and I think we can provide you with some good references. Yeah, simplified description are very useful, but I recommend the audience just to know and remember what are the limits of these simplifying descriptions, and particularly the hypothesis, not to apply these models to situations where they cannot be valid. And of course, more developments and examples of these basic aspects would be presented and discussed during the workshop to come soon. And with that, I thank you for your kind attendance. I'm very sorry to have passed the time, and I would be very pleased to discuss with you during the workshop in Reims, but we might have time here with our moderator, Professor Hitchcock, to have some discussion right now. Thank you very much.